There's just one more thing I want to do in this module 6 on optimal estimation. This video only covers two charts, two view graphs. And there's this thing called General Minimum Variance, which says, here's our cost function, which is this weighted sum of errors given a set of measurements. And our job is to minimize that. And here, well, x hat is our estimate of x, and x now is itself a random variable. Everything we did up to now was not a random variable. Now the thing we're estimating is a random variable based on random variable measurements, random measurements. So this x tilde means the difference between our estimate and the true x, which are error. So it's kind of a mean square thing up here. Q is a weighting of those errors. All we require is that it be symmetric and invertible. Z is the set of estimates. And I'm going to skip, well, all derivations. See my website if you're curious. It says, here's the answer. The optimal x, the thing that minimizes this j, is the expected value of x given a set of measurements, which would then mean this is the variance, so we get a general minimum variance. Because this means the mean of the error is 0. And that problem has what came across to me as rather remarkable results. First is just this result. The minimum variance estimate is the conditional mean, this thing here, which means it's also an unbiased estimate. Just get that out of it. Here is what seems rather remarkable to me. If you just looked at this and said minimize that, would you think the answer would not depend on Q? It doesn't matter on how you weight them. You still get, here's the same optimal answer. So pick anything you want for Q. So why not pick something easy, like the identity matrix? It's symmetric and it's invertible. So what we're doing, well, let me kind of jump to the conclusion first. That minimum variance, which had that J cost function on the previous chart, well, all these criteria for optimality are equivalent. Minimum variance turns out to be the same as minimum mean square error, which we talked about before, which also minimizes the trace of this covariance matrix, and also the conditional mean. All these things are really the same thing. They're the same measures of optimality, which I think is pretty remarkable. Some of this, that the trace, some of the mean square errors and the trace, that they're the same. It's just kind of an outcome of the way the matrix or vector arithmetic works. Here's the covariance of the errors. The covariance matrix of the error. It'll look like this. What does the trace mean? It's the sum of the main diagonals. So if I minimize the trace, take my word for it, it's the same as minimizing the mean square error. So when we get to the Kalman filter, we're going to be using this as kind of the underlying theory. The Kalman filter is going to use a blue method, best linear unbiased estimate. It will minimize mean square error, but we're actually going to compute it or derive it by minimizing the trace of this covariance matrix. That's just a look ahead of what's coming up in module 7. Two charts to me are kind of heavy and a little bit mind-blowing to me. But it sets us on a good footing to start Kalman filter. Now we'll finally get to the Kalman filter in module 7. Thumbs up.